Hello viewers, welcome to the Raspberry Pi Programming in Proteus tutorial series, episode 3. If you are following along this tutorial series, you will know previously we have covered the basics of setting up Raspberry Pi in Proteus, and in our previous tutorial, episode 2, we have seen how we can use digital output and digital input in Raspberry Pi. In this tutorial, we will see how we can take the analog input from the Raspberry Pi. So if you are coming from Arduino, or if you have programming experience in Arduino or AVR microcontroller or any other microcontroller, you may know that there are some separate pins called the analog pins, using which you can directly take analog input. So you know that most of the sensors or some of the sensors are analog sensors. They provide value in analog form, but the problem is the microcontroller, it cannot read the analog values, so there needs some IC that is called analog to digital converter, and in case of Arduino or AVR microcontroller, that IC is built in, so we don't need to do any additional work. We can directly take input from the microcontroller. But in case of Raspberry Pi, you know, it's a computer, so it does not comes with a built-in analog to digital converter IC. So to take analog input from analog sensors, we need analog to digital converter IC. So for that, we need a IC called MCP3208. It's an analog to digital converter IC. We will see in later in this tutorial that how we can connect it and how we can read data from it. So the outline of our today tutorial is first we will see the short introduction of MCP3208, and then we'll see how to set up the circuit diagram, and after that we'll understand how the data is being transmitted from the MCP3208 to the Raspberry Pi. Okay, so this IC here, this is MCP3208, and you can see there are channels. There are total 8 channels. So you can connect 8 different analog sensors in these channels, and you can read at a time value from all of these sensors using the Raspberry Pi. So here are some other pins. That this pin, 16 number pin, this is the power pin, and VREF, this is the reference voltage. If you have a little understanding about the analog reading, then you may know that it requires a reference voltage. For Arduino, it is a 5-volt IC, so the reference voltage is 5 volt, but for Raspberry Pi, it's an ARM based processor, and the working voltage for this IC is 3.3 volt. So in this case, the reference voltage will be 3.3 volt, and the AGND pin, you can connect it or not. These 4 pins are important: CLK, Dout, DIN, and CS. These 4 pins will be connected to the Raspberry Pi using the SPI interface. So we'll talk later in this tutorial series about the communication methods, but we need serial peripheral interface for this tutorial. So we'll just understand how it works, and later I will upload a descriptive video about how to set up the SPI and how it actually works. So this IC, this is an analog to digital converter IC, and it has a resolution of 12-bit. It means it can represent the data, the voltage read in the range between 0 to 3.3 volt, in the range of data between 0 to 496. So it will give you a value of for a particular voltage, it will give you a digital value of something like this. And as we discussed earlier, it used SPI communication to transmit the data to the microcontroller. So now let's go to the Proteus and see how we set up the circuit. Okay, so here we have taken the MCP3208 IC. You will find it in the Proteus components library, and we have taken the potentiometer as an analog sensor here, and as you see, we connect here. This is a DC power source. We need to provide 3.3 volt to the IC. So the VREF pin, it is connected to the DC power source. If you see it, you can see the voltage rating is 3.3 volt, and the potentiometer also needs to be connected with the 3.3 volt power source, and the middle pin, the wiper pin of the potentiometer, I have connected it to channel 5. You can connect it to any channel, you just need to change it into the code. And here these are the four most important pins. The CLK pin, the CLK pin needs to be connected with the CLK pin of the Raspberry Pi. The MOSI pin needs to be connected to the MOSI pin of the Raspberry Pi. MISO to the MISO, and the CS pin, you can connect it to any GPIO pins. You need to control it manually, so I have connected it to the GPIO 12. You can connect it to any GPIO pins. Okay, so this is the circuit. Now let's see the coding. First, you need to import the SPI dev library. This library deals with the SPI communication. Then the time library and the Raspberry Pi.gpio library to control the GPIO ports. And we have set it to gpio.bcm GPIO mode. You can choose any mode. If you have seen the previous video, you can you know that we can also use it as gpio.board. So in this case, I am using gpio.bcm, and these are the SPI setup to use the SPI options. And the chip select pin or the CS pin is connected to the GPIO 12, and we need to set it as output. Okay, now we need to set up the reading function, how we read the data from the MCP3208. So the way it works is to read data from MCP3208, you need to send 3 bytes of data to that chip. So in it contains total, most of the informations are not necessary. Only the necessary informations are let me show you, are these pins. If you see the data set, you will understand it more clearly. These pins are these data bytes are most important. So the D2, D1 and D0, these 3 bits represent the channel, which channel you will be using, and these 2 bits for the first and the second bit, these 2 bits represent, this bit represents the start bit, and it represents the reading mode, which mode you are using. So by default, you can take these 2 bits as 1 and 1. You don't need to change these 2 bits. You can keep it 1 and 1, and these 3 bits will be changed depending upon which channel you are using. So let's get back to the code, and as you can see here, spi.xcfr2, in this function we are sending a list, and inside this list you can see there are 3 different data. This is 1, this is another, and here is 0. So the third byte, you can set it to 0. You don't need to care about this one, but these 2 are most important. So what we are doing here, so when we will read data from a channel, let's say we want to read data from channel 5. Okay, so what you need to do, you need to divide these bits. So how we represent the data? So if we go back here, so as you know that the binary for 5 is 1, 0 and 1. Okay, 1, 0 and 1. So if you see, first we are performing a OR operation, 6 or channel write shift 2. So what does this mean? So channel write shift 2 means if we make it a 8-bit form, so we get something like this: 101, 0, 0, 0, 0, 0. So 5 zeros in the front and 3 for 101 or 5. So when we right shift it, if you know that if we right shift it, so these two bits will be shifted and we will get something like this: 0 0 0 0 4 0, and here 0 0 0 and 1. So this is the D2, this is D2 pin, this is D1, and this is D0. So we only have D2 here. So you might think, where will these two bits go? So we'll take care of that later. So we have just retrieved the D2 bit here. Now we need to perform OR operation with a number. So if we see here, we are performing OR operation 6 and OR operation with that bit. So what we will get, the writing, okay, so 6, okay, so the binary representation for 6 is 0 0 0 0 4 0 and 0, sorry, 1 1 0, and here another 0. This is the binary representation of 6, and if we perform OR operation with the right shifted, we just right shifted the number, we'll get 0 0 0 and 0 0 0 1. So what is the output? The output will be OR operation 0 0 0 0 and zeros, here 1 1 and 1. So this is our third bit. So this bit, you can see we have achieved what we want to do. So these two bits are by default 1, and the D2 bit depends on the channel. So for channel 5 we get a 1 on here. So this is the third bit, and we don't need to worry about the sorry, this is the first byte, and we don't need to worry about the third byte. The third byte all will be these are you can set to 0 or anything else, it does not matter actually. So we have to take care about the second byte. So for the second byte, you can see here the third byte, it is set to 0, and for the second byte we are left shifting the channel value by 6. So I just take another here, and the channel value is 0 0 0 0 and 0 1 0 1. So if we left shift it by 6, left shift by 6, so after left shifting we'll get something like this. So this is our second byte. So these values will be set to 0 when we set this here, set this value. So you can see that we get 0 1 here and 1 here. So what is our channel? Our channel was 5, that means 1 0 1 0 1, and the combination of these three, sorry, combination of these three, it actually becomes our channel 5. So this was what we are doing in here. So this is the way to tell the chip that we want to read data from the channel 5, and where one will be one bit will be for start bit and another will be for the reading mode, and this will send a data back. So the data will also be 3 byte data, and it will be an array of 3 bytes. So what we are doing in here, first, if we see here back, the first byte, this is not important when the data is transmitted back from the chip. This is not important, you can just avoid it. And this is the second byte. So for the second byte, these 4 bytes are the, sorry, these 4 bits are the data bit, and for the third byte, the whole 8 bit is the data bit. So if you recall, the MCP3208 is a 12-bit resolution analog to digital converter, but we know that in case of the data communication, we are using 8-bit data, so we cannot represent 12-bit inside 8-bit data. So that's why we need two registers. In the second byte we have 4-bit, and in the third byte we have another 8-bit. So first we need to retrieve this portion. Okay, we need to retrieve this portion. So if I just make it a little longer, so what we're doing here, you can see that ADC 1 and 15. So with the second byte, or as the index is 1, the 0 is the first byte, 1 is the second byte. So 1, we are performing AND operation with 15. So what we are doing here, let's take the text. Okay, so let's say there are something on the first 4-bit, we don't know what are in there, the most significant bits, and inside the least significant bits we have let's say that our microprocessor, our chip is sending us this value 3056, the value read from the processor. So the binary representation of it will be 1011 and 1111 and 40. So this will be our binary representation. This is the chip sending reading from the sensor. So these 4 bits will be stored inside here, and the other 8 bits, it will be on the third data byte. So now let's get back here, and okay, so let's say we have something like this 00 and 1011. This is our second byte. So we are performing AND operation with 15. So the binary value of 15 is 1111. So when we perform the AND operation, we'll get something like this 1011. So by this method, we are ignoring the first 4-bit what are there, and we will just we're just extracting the 4-bit that is our data. So we have extracted it now, and now let's get it back, and we are now left shifting it by 8. So left shifting it by 8 will give us 1011 00000000. So this will give us something like this. So as you can see that our data here 3056, we have get the most significant 4-bit, or the 9th, 10th, 11th and 12th bit of the data. Now we just need to retrieve the lower portion, the third byte of the data. So how will we get that, the third byte of the data? So as you can see here, we are just performing add OR operation, or add with the third byte. So if I just extend it, and if you just perform OR operation with the third byte, you will get okay. So sorry. Okay, so if you see here that we have extracted the data that was sent from the chip. So this was all about the reading the data from the chip, and now if you want, you can convert it to voltage, the data to voltage, or you can use that data, it will change accordingly with the value of the sensor. And now we are returning the ADC value. So our ADC setup, ADC coding is done. Now inside the while loop, first we'll set the chip select pin to low. This is the way of reading. First you need to set it to low, and we are reading from it, analog read, and this is our channel 5, and after that we need to set it to high again, and here we are printing the value received from the chip as the output. So now let's run it. Okay, so let's change this value. Okay, so in the simulation log here you can see the value of the voltage. You can bring it to our main window, just drag it and make it a little small, and let's go back to the okay. So now if you you'll see that if we change this value, the value of voltage is also changing. It is giving us the value from 0 to the maximum of 3.329, or we can say 3.3 volts. Okay, so this way we can get the voltage reading, analog voltage reading from a sensor. And if you want the analog value, then you just need to just turn it off, and from here you can just return the data instead of the value. And let's turn it again. Now you can see that we are giving the sensor is giving us the value in the range 0 to 4096. So if you can see the maximum is 4091, close to 4096. There are small data loss, and if we reduce it, you can see that the minimum is 5. So this is our analog value. Okay, and if you bring the simulation log back, so you just drag it here and put it here. That's all. So that is all about analog reading in Raspberry Pi. I hope you have enjoyed this tutorial and you will find it helpful. So please like the video and subscribe and share. Thanks for watching.